In the previous lessons, we built the mathematical toolkit for electromagnetic theory, gradient, divergence, curl, coordinate transformations, and the divergence and Stokes theorems. Now we begin electrostatics, the study of electric charges at rest and the fields they create. In this lesson, Coulomb's law, the electric field concept, and the superposition principle. Coulomb's law describes the electrostatic force between 2-point charges. If charge q₁ sits at the origin and charge q₂ sits at position r, the force on q₂ is F equals q₁ q₂ divided by 4 pi epsilon 0 r squared in the direction of E hat r from q₁ toward q₂. Epsilon 0 is the permittivity of free space, 8.854 times 10 to the minus 12 farads per meter. The constant k equals 1 over 4 pi epsilon 0, approximately 9 times 10 to the 9 Newton meters squared per Coulomb squared. If both charges have the same sign, the force is repulsive. If they have opposite signs, it is attractive. Let us compute a quick example. Charge q₁ equals plus 3 microcoulombs at the origin. Charge q₂ equals minus 2 microcoulombs at position 0 for 0 meters. The separation r is 4 meters. The force magnitude, F equals k, times the product of the charge magnitudes divided by r squared. That gives 9 times 10 to the 9 times 6 times 10 to the minus 12, all divided by 16. The result is 3.375 millinewtons. Since the charges have opposite signs, the force on q₂ is attractive. It points toward q₁ in the minus y hat direction. Now we define the electric field. Place a tiny positive test charge q at some point in space. It feels a force F from all the source charges. The electric field at that point is E equals F divided by Q. The electric field tells us the force per unit charge. It exists everywhere in space, whether or not we place a test charge there. For a single point charge q at the origin, the electric field at distance r is E equals Q divided by 4 pi epsilon 0 r squared times E hat r. If Q is positive, E points radially outward. If Q is negative, E points radially inward. The magnitude drops off as 1 over r squared. The superposition principle states the total electric field from multiple charges is the vector sum of the individual fields. For n-point charges, E total equals the sum from I equals 1 to n of qi over 4 pi epsilon 0 ri squared times E hat ri. Let us verify with an example. Two equal charges, each plus 1 microcoulomb, placed at minus 1, 0 and plus 1, 0 meters. Find E at point P equals 0, 1. The distance from each charge to P is the square root of 2 meters. Each field has magnitude K times 10 to the minus 6 over 2, which is 4,500 newtons per coulomb. By symmetry, the horizontal components point in opposite directions and cancel exactly. The vertical components both point upward and add. The vertical component of each is 4,500 over root 2, approximately 3,182 newtons per coulomb. Total E equals 6,364 E hat Y newtons per coulomb. Symmetry simplified the entire cut. Let us review. Coulomb's law, F equals K q₁ q₂ over r squared in the E hat r direction. The electric field, E equals F over Q. For a point charge, E equals K Q over r squared E hat r. The superposition principle lets us find the total field from multiple charges by vector addition. In the next lesson, we extend these ideas to continuous charge distributions lines, surfaces, and volumes of charge.